All right, it's time to get excited because example 1 presents us with our very first Maclaurin series we're going to generate for f of x is equal to sine x. So step number 1, what we're supposed to do is take a whole bunch of derivatives of sine. So I'm going to start with just writing down sine x and then take its derivative, which I'm pretty sure is cosine x. Second derivative is negative sine x. And the third, negative cosine. And what's the derivative of negative cosine? That is, well, let's make this equal sign look prettier. Anyway, that's cosine sine, and then you can see that it just basically loops back to the original thing. So that's enough derivatives, really, because it is enough to establish a pattern. So now I have to evaluate each one of these at, since it's Maclaurin, specifically at 0. So f of 0 is equal to the sine of 0. The sine of 0 is 0. And then I'm going to evaluate the cosine of 0. Cosine of 0 is 1. And then I already know this one's going to be 0 because it's sine of 0. Doesn't even matter. It's negative 0. Come on. Yes, it is. All right. And then the third derivative at 0. Again, the cosine of 0 is 1. I'm just making it negative this time, and then we're back at sine again, which means that that one's going to be 0. So I can carry on this pattern. I can see that the next one is going to be a 1, and then a negative 1. No, it isn't. It's going to be a 0, and then a negative 1, and then a 0, and then a 1, and then when should I stop? I think that's probably enough. Okay, so that's enough in order to establish a pattern of our little coefficients, and then we're going to start writing our Taylor series, not a polynomial, like this. So our f of x is equal to, so our first, we're going to evaluate the function first of all, so that's going to be 0. I'll write it down even though it's just 0. And then plus, we want to find the first derivative and then multiply that times x. So the first derivative is 1, and then multiply that times x. And then plus, we're going to evaluate the second one and multiply it times x squared. So the second derivative was 0, and that's supposed to be over 2 factorial times x squared. And then plus, then we want the third derivative. So the third derivative was a negative 1. So negative 1 over a 3 factorial times x to the third plus, and I'm pretty sure the next one is a 0 over a 4 factorial, x to the fourth, and then plus, my next number in my little pattern here is 1 over 5 factorial, x to the fifth, and then, you know, so on and so on. So let's simplify this a little bit by getting rid of all the 0 terms. F of x is equal to, starts off with an x, there's no x squared term, minus 1 over, actually I'll write that as x cubed over 3 factorial. Okay, and there's no x to the fourth. Next one is going to be plus x to the fifth over 5 factorial. And then I'm going to carry on this pattern here. I know it's going to alternate in sign here, so this one's going to be negative. I'm going to skip the sixth one because that's what's going to be 0. 7 over 7 factorial. Can you guess the next one? X to the ninth over 9 factorial. And then minus dot, 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 whatever. Right? Keeps on going. So now we want to establish some kind of pattern so we can generalize this thing and write it in summation notation. So remember, whoops, that we're going to start this one with an n equals 0. So that's why we got rid of all those 0 terms. This one's not the 0th term. This one is going to be the 0th term. This is going to be n equals 1, n equals 2, n equals 3, n equals 4, and so on. And now what I want you to notice now is all of our exponents, they're all odd numbers. If they're all odd numbers, then they should be able to be written as either a 2n plus 1 or a 2n minus 1. We'll just have to see which one fits here. So if I stick in here, let's pick one at random like 2. So 2 times 2 makes that 4 plus 1 is indeed 5. So I am going to use this one. All right, so that is not only the exponent, but it's also the factorial down here at the bottom, since those numbers are exactly the same. All right, so to generalize then, f of x is equal to sine x, which is equal to the sum from n equals 0 to infinity. Don't forget that we have this negative, like the alternator. We need an alternator in here. We'll have to figure out what the power on this thing is going to be. Let's try n first of all. If I plug in 0, negative 1 to the 0 power makes that just a positive 1, and we start off with a positive number. If I stick in 1 here, negative 1 to the first power is negative, and I get a negative, so that works out perfectly. Now we have this little fraction here. It's x to our odd powers, which is 2n plus 1, and then it's over the 2n plus 1 factorial. Ta-da! We have ourselves a Taylor series, Maclaurin series, specifically for sine x, and the only thing left to do is the interval of convergence. So we have to perform the ratio test on it. So let's take the limit as n goes to infinity of the absolute value of negative 1 to the nth plus 1. Everywhere there's n, I'm going to add a 1 to it. X to the 2 parentheses n plus 1 over, and then the same deal here. So 2 n plus 1 plus 1, all of that factorial. And then we'll multiply by the reciprocal. So on top is a 2n plus 1 factorial over negative 1 to the nth, and then x to the 2n plus 1. Okay, go ahead and get out your cancellation crayon, because I think there's going to be some stuff canceling, like these. Who cares about the alternator? We took the absolute value. Let's go. All right, and then let's rewrite this exponent here. That'll be a 2n plus 2, but we're going to add 1 to it, so it's really a 2n plus 3, which means this down here is also a 2n plus 3 factorial. Okay, so as far as those factorials go, it's a 2n plus 3, subtract 1 from it, 2n plus 2, subtract 1 from it, 2n plus 1 factorial, and those cancel. So we're still left with these two terms. Right, and then the powers on the x, we're going to subtract these two things. So 2n plus 3 minus 2n plus 1, the two n's will cancel, and it's just essentially 3 minus the 1, which leaves us an x squared. So this whole thing simplifies to not having enough room, simplifies to limit as n goes to infinity of only thing left up top is an x squared. Absolute value. Do you really need it? Probably not. Over 2n plus 3 and 2n plus 2. Now I took it out of the absolute value. It should actually be in there, but I took it out because you know why? It's positive. Those are positive numbers. Okay, so remember that n is the variable for the limit. X is not affected, only this denominator. It's getting infinitely big as the absolute value of x squared stays the same. So this is going to shoot down to 0, which is less than 1. What does that mean? That means that this thing converges for all real numbers. The domain of this power series, which is technically the Maclaurin series, it's going to converge to sine x for all values of x. So, for example, if I wanted to evaluate sine for a particular number without a calculator, or maybe even program this into the calculator so it calculates it correctly for us, it's going to approximate this thing basically with a Taylor or Maclaurin polynomial, because it's not going to do an infinite number of terms. But I would just plug my number in there, sum up a whole bunch of them, and it's going to give us a really accurate approximation for the sine of that angle, whatever that angle is here. I've got some pictures for you. So here's all of that, what we just did, and we established that pattern. We used the ratio test and we found this. Okay, so here's some pictures. So obviously we can see the sine x graphed, and then here is the first degree Taylor polynomial, Maclaurin, and then the third one, we don't have a second one because that second degree term just disappeared, and then the fifth one, and then the seventh one. Here's a little animation playing this thing out. Okay, so why start at the 19th one? Should have started at 0. All right, well, or 1, whatever. All right, so it's going to loop back around. Just give it a minute. Okay, there we go. So here's sine, and then here's our first degree, our third degree, fifth, and then so on. And you can see that as the animation continues, it's hugging the sine x graph closer and closer and closer for longer and longer intervals, all the way up to, what did it stop at, like 21 or something? No, 23? 25? 27? Oh, okay, it goes all the way to 29, but man, look, that's pretty fantastic there, approximation for sine x. All right, but this is not quite finished. Let's take this one step further. Find the Maclaurin series. F of x is equal to sine of x squared. So we know from the last lesson, the only thing that we need to do is do a composition. Let's do that composition here. So since we're doing sine of x squared and we already have the sine of x, we're going to take f of x squared is equal to sine of x squared, and all we have to do is in our nth degree term that's right there, just plug in an x squared where there is an x. So summation from n equals 0 to infinity. -1 to the nth, that is not affected. We're just plugging stuff in for the x's. So I have an x squared here to the 2n plus 1 power, that odd power, over 2n plus 1. Oh yeah, before I forget, odd powers. And we always consider sine to be an odd function, right? There's a connection between those two things as well. All right, and you could leave it like this, but we usually don't because we can do a power to a power right there and then simplify that thing too. Say 2 times 2 would be a 4. My eraser is turning into a laser pointer. So that would be a 4. And now my pencil won't cooperate. I'm telling it a 4 and it's writing a 2. N plus, and then let's see, 2 times 1 plus 2. There you go. And you could expand this thing out, and whenever you expanded this thing out, let's say, for example, I were to stick in a 0. So plugging in a 0 into your alternator makes that 1, so it's good to go. It's going to be positive. And if I plug in a 0 here, that's gone, and I'm left with a 2, and it'll be the first term in x squared. And if I plug in a 2 down, or a 0 down here, that just makes 1 factorial, so it's just x squared. Why did I write it up in the air? Probably because I thought I was going to write a fraction. Okay, the next one, if I stick in the number 1, -1 to the first power, it's going to be negative. It's going to start alternating. And then whenever I stick in the 1 here, that's going to be 4, plus 2 is going to be a 6. X to the 6th, sticking a 1 in here, that's going to be a 3 factorial. And that, notice that I could get the same exact thing from this expansion right here. If I had f of x squared, just plug in an x squared here. So I'd have x squared minus, this is x squared cubed over 3 factorial, and you multiply power to a power, you're going to multiply, that's going to make that to the 6th. Again, that's exactly what we got right down here. And then plus x squared to the 5th over 5 factorial, power to a power, 2 times 5 is x to the 10th, and so on.